speculate a word that we have that has the PET in it?
Pet.
Pardon?
Like your pet dog?
No, I don't think that thing is completely different.
Petrified?
Ooh, I thought about that one. I suspect not. I think.
Wait, can you ask the question again? I'm sorry.
Another English word that has PET in it that deals with things coming towards each other.
Okay.
Petrol?
No.
I think we're thinking of all the things that you're not thinking of.
No, that's for sure. So far, so good.
Does it start with PET?
Not the one I'm thinking of.
Oh, okay.
Apparently, it's a mind reading lesson here. All right, I'm going to spoil it. Sorry. Competition.
Competition.
Competition has the same basic root. You have two teams coming together.
Okay.
What are they seeking?
They're seeking victory.
What do they teach? What do they seek?
Seeking, sorry.
They seek. The reason it's called centripetal acceleration is the acceleration is pointing towards the center. It is not pointing away. It is pointing towards the center. So the acceleration is in this direction. Depending on where it is on the circle at that moment. We can look at it also from the point of view that acceleration is the change in velocity over change in time, just looking at it from sort of an average point of view. So if I'm on my circle, and I need more room. Let's move that on. So if I'm on the circle at this point, my velocity is pointing in that direction. It's supposed to be tangent. And just a moment later, my velocity is pointing in that direction. So we'll call that initial velocity and final velocity. The change in velocity will have the same direction as the acceleration. I know that this is v final minus v initial, because that's what change is. In other words, if I v initial plus my change in velocity is equal to v final. So if I draw my v initial and I draw my v final, my change in velocity, head to tail method, vi plus my change in velocity, that is towards the center.
Dr. Fox?
Yes.
When you're calculating the change, is it drawing a straight line between the 2 points, or is it like the radius value?
Ask that again?
So you drew a line to represent change of velocity.
Yes.
So is that a straight line, or is it like the radian circular value?
It is a straight line.
Okay.
Yeah, because I'm just doing very simplistic.
Perfect.
Now, there are a couple of videos where I go through the derivation of centripetal acceleration. It's not planning to do the derivation right now. But we have centripetal acceleration. The magnitude of centripetal acceleration is the speed squared divided by r. R is the radius of the circle, and v is how fast you're going. And that's also equal to omega squared r. So I'm going to use this to talk about omega. So I guess two things. One, also, I will say centripetal. It sounds a whole lot like the word that should not be used here, centrifugal. I know Massason does much more pronounced. I think it's more the British pronunciation of centripetal and centrifugal, because it's a lot clearer there. But do not confuse this with the other one. So we're gonna write this up here and then erase it, and hopefully it will never come up again. Center, this is fleeing.
Oh. Oh, so it's not like that. It's the opposite. That's what
It
that would
is.
say to me.
It is the opposite. All right, so English word that has F-U-G in it, that means fleeing.
Fugitive.
Yeah.
Yes. And there's also a Latin expression which I see pop up in shows occasionally, tempus fugit or fugit. That's one of how true they want to be to which era. But it means time flies. Tempus fugit, time flies.
Up there, next to V squared over R, what is that A of?
A sub C.
Oh, okay.
All right, so there are proper ways to use this. Most people do not use centrifugal properly, and so you probably do well never to use this word again. Some textbooks will label the force associated with it to be a fake force or a false force. That there's the illusion in certain reference frames, like Coriolis force. All right, this omega. Well, V is the basically distance divided by time. If I have something that's swinging in a circle, well, the distance that's traveled, if I'm going, what is the distance traveled if I'm traveling in a circle?
2 pi r.
That's the one. So if I'm talking about an entire circle here, the time it takes to do any repetitive motion once is called the period.
Oh, okay.
And so if you were timing something, how long it takes something to go around in the circle, you could time it, say, 20 times. So it'd be 20 times 2 pi r divided by however time it does it, and you have a general average speed. Now, if I look at 2 pi over t times r, this right here is basically omega.
Oh, yeah.
But what is 2 pi in terms of a circle?
The whole circle.
Be more specific, or did I miss something?
The diameter? No.
360 degrees.
36, yeah.
So what is 2 pi?
The
Oh, the radius of the whole circle.
Okay, it's, yeah. So radians,
radius. Okay, that's the
if you're dealing with radians. All right, so it's the angle of an entire circle in radians. Why? What's a radian?
One.
Half a circle.
Isn't it like pi over 180 or something?
Okay, then why is it pi over 180?
The measurement of the distance of the circumference.
Measure the distance of the arc length?
Yes.
Okay, so what about the arc length?
That's what radians represent. Is like if you, let's say you put it at a certain angle and then you make that compared to the x-axis, then the radian value is just the distance of the arc length that the triangle makes.
That there won't be a triangle.
Except it's like a pizza shape or something, I don't know.
Okay, the wedge.
Yeah.
All right, you're hitting close to it. You're seeing the ballpark. There are a couple things that all circles have in common.
The round.
Okay?
Okay.
We're assuming Euclidean space here, so yes. Anything else that all circles have in common?
That 2 pi. They're all going to be, regardless of the size of the radius, they're all going to have that 2 pi in common.
Like the
Okay.
relationship between pi and like the circumference, for finding the circumference is always the same formula, finding the area is always the same formula. Like the relationship is the same.
Okay.
Variables.
And the one thing that those two formulas have in common is the radius. All circles have a radius. So there's an attempt by mathematicians to take all humankind out of math to try to get it down to what is truly the purest of math. And so with a circle, all circles have a radius. And if you take something of arc length of that radius, and this gets to what I was hearing you say, is that if you wrap that radius around for the arc length, that is 1 radian. The arc length that is, I think subtended is the right word, the arc length that is subtended, sorry, the angle that is subtended by having an arc length of 1 radius. And since there's 2 pi radii going around a circle, 2 pi r, there's 2 pi radians. And so you can work it out a little bit more, and you can end up with that the arc length is equal to r theta. So the arc length is equal to the radius times the angle in radians. SRO. Sort of. So if I have something traveling in a circle here, so if something's traveling around in a circle, well, if I look at S, well, ds dt, that's just my speed. So if I had some object here that's moving around in the circle at some particular speed, I can figure out my speed just by doing a derivative of where they are on the circle. And that should be equal to the derivative of r theta dt. R is constant. So I end up with the speed being equal to r times d theta dt. So angle here is basically the analog, the rotational analog of distance. And so the derivative is the rotational analog of speed, which is known as angular speed, or rotational speed, either one works. And based upon your knowledge of math and life, what are the international standard units of omega? This is an omega, by the way. It is not a W.
Oh, it's not a W. Dang, I was calling it W this whole time.
Oh, it is an omega.
So it's an angle, so it'd be radian meters per second. So whatever your number is. No, do we have to do that notation? We do the, and then we put the, well, we get a meters per second, comma, and then the angle radian.
Oh, I'm not quite sure which notation uses to do that.
I forgot what we were doing earlier. It was a comma.
Oh, that's polar notation.
Oh.
Yeah, no, we're not doing polar notation here. Units.
Do we have a hint? Is there something I should be thinking of to make me think of angular speed?
Well, what are the units of speed? The SI units of speed.
Meters per second.
Radius?
Meters.
Okay, so what does omega need to be in order for this equation to work?
1 over seconds.
Now, the trouble is saying just 1 over seconds. And that's not wrong. It's just traditionally not the way it's written. The trouble with that is we'll eventually get into frequency and angular frequency. And frequency is sort of 1 over seconds. Angular frequency could be 1 over seconds, but it's really not. And so there's some confusion that shows up later on if you ignore radians.
Is it seconds to the -1? Is that what you're looking for?
No, I mean, that's the same thing as 1 over seconds. Typically, the unit of omega, you would write it as radians per second. Now, if you just wrote seconds to the -1 or 1 over seconds, it's not wrong. I would not take off for that. But by leaving radians out, there's potential confusion later on.
Okay, that makes sense.
You guys, so omega is also the exact same thing we use for angular frequency, which has units of radians per second, as opposed to the units of frequency, which is 1/seconds or hertz. This is not hertz. There's some other fun unit things where you have Newton meters later on, which is joules in some cases, but not in others.
Oh, that's how they got that many.
So let's do just a quick plug and chug. I'm going to, let's say, going around a circle of radius 5 meters, and I do it on an average of, let's say, 2 seconds to go around the circle. What is my acceleration? Let's solve it both ways. What's the distance traveled?
2 pi r.
So 10 pi, 31.415 meters. My period is 2 seconds, and so my acceleration is, let's find V first. So V is 31.4159 divided by 2. 15 point.
I got you. 31.1 divided by 2. 15.70795. Yeah.
All right, meters per second. And
Dr.
so my,
Fox, oh, sorry.
go ahead.
Dr. Fox, just to clarify, that's speed, right? That's
Yes.
not a vector.
Correct. That is speed. And over there, the formula, there are no vector symbols on this over here for a reason. So my centripetal acceleration, the magnitude of my centripetal acceleration is 15.71 squared divided by 5. Something.
49.347 meters per second squared.
Let's go. So you're experiencing almost 4 Gs. No, almost 5 Gs.
What is a
lot.
G?
What is a G?
Normal, if you're in free fall,
Yeah.
that you'd be experiencing 1 G. If you hear about acceleration that objects take, I've seen it usually in terms of astronauts during takeoff, how many Gs. It's basically what the acceleration due to gravity feels like to them at that moment.
5 Gs is a lot though. I saw a Formula 1 racer that took a crash that was 5 Gs. The car did not look too hot.
Yeah, and there's I don't have the information with me here. There's a place I found the number of Gs you can go before you black out, and the number of Gs you can take before you die. And,
Like in Top Gun, Maverick experienced 10 Gs.
Wow.
now the fighter pilots have special suits to keep the blood, because if I'm doing a dive like this, wearing this, the blood basically inertia. The blood wants to be going straight, and my body is not, and so the blood will basically just shoot down. From my point of view, and I would not have any blood in my head. That could kill.
If you lived, I feel like you'd cry about it for a couple days. That sounds horrible.
Yes.
Least your concerns.
Not to mention what it would do to your brain, but I think fighter pilots are a little bit crazy to begin with. All right, I'm doing it the other way. Omega, this is my angular speed. It's angle divided by time. So in one rotation, it's 2 pi radians divided by my time, which is 2 seconds. And so my omega is 3.14159 radians per second. And so 3.14159 squared times my radius of 5. That's something spectacular. Oh, it should be, I'm thinking somewhere around 49.347.
Yeah.
Meters per second squared.
Yeah, 49.
Now notice my radians disappeared because this was radians per second, this was meters, and I just decided not to write radians. It is a unitless unit. Because if we go back to this formula over here, S equals R theta, S is a distance, it's an arc length, meters. R is a distance, meters. So I have meters is equal to meters times something, 1. But we call it radians. So a radian you put in when it's convenient, and you take it out when it's convenient. I had a student a number of years ago who always stuck radians at the end of every single answer. Because it was not technically wrong.
Even if it wasn't like related to radians.
Right.
At all?
Right.
Because it's applied? Okay, that makes sense.
Typically you don't do that, but you know, again, I would say it's not technically wrong. Right. Questions to hear?
Actually, is this the knowledge we're going to be working with next lab?
The next slide was the projectile motion stuff. The stuff that we did at the very beginning,
Yeah.
before I got into
Oh, so that's going to be in 2 days on Wednesday. We're going to be dealing with.
the shooting stuff.
Okay.
Can I just ask really quick? It's the lab that says projectile motion part 1, right?
No, there's linear motion part 1, and then there's projectile motion.
I meant linear motion. Is that the
Yeah.
one I was supposed to hear?
The linear motion, I guess there are a couple places where this might relate. The linear motion lab is the one that's due next Monday.